Hello and welcome to PT and Nutrition Education's e-learning platform. Today we'll be continuing our preparation for the examination in anatomy and physiology, and as you can see, the topic in question will be related to the energy systems. So today the objectives that we'll cover are describing the use of ATP in the human body. ATP stands for adenosine triphosphate, but we'll talk more about that in the upcoming slides. We're then going to identify the key characteristics of the three energy systems that the human body has. So that's the ATPPC system, the lactic acid system, and the aerobic energy systems. And thirdly, we're going to understand the energy system's function in relation to sport and exercise. So the interplay between these three energy systems and when they are predominant during exercise. Now, this lecture is no different than the previous lectures. Along the way, we will be setting interactive tasks and worksheets, which we expect you to complete. So we do encourage you to take part in those, pause the video whenever we ask you to, and to complete those so that you are better prepared. You can embed your learning and consolidate that in preparation for your exam. So without further ado, let's get cracking on the energy systems. Now, in order for our muscles to work and provide movement, energy is required, and this energy comes in the form of what's known as adenosine triphosphate. And adenosine triphosphate is the energy currency of the body. It's the only usable form of energy that our body can use in order for movement to occur. In terms of the molecular makeup of adenosine triphosphate, we can see from this diagram here that, as the name suggests, it's made up of a adenine molecule, which is in blue here, and then three phosphate molecules, so hence the word triphosphate. And in between these phosphate bonds, there is high energy which we need to break down so that the body and the muscles can use them for contraction. This thing here is called ribose, and this is a sugar which simply just connects adenine and the phosphate groups. But this is beyond the scope of what you need to know for your level 2 and level 3 examination. Now, the great thing about ATP is that this is stored energy that we can call upon when we need it. And once those high energy bonds have been broken down, they also can be reversed. So we can take part in a process which is known as resynthesis. But we'll talk more about that as we divulge into the different energy systems. For now, all that we need to know is that ATP provides the body with a continual supply of energy for exercises of all intensities and durations. So this is just basic muscle physiology and energetics when it comes to how the body is provided with energy through the form of adenosine triphosphate. Okay, so let's have a look at ATP in action. Now, as we've mentioned in the previous slide, adenosine triphosphate is made up of a adenine molecule, adenosine, and three phosphate bonds. Now, in between those bonds is high energy, which we need to access as and when the muscles need it. Now, in order to access that energy, we need something to break those bonds apart, and the body is equipped with enzymes in order to break specific bonds so that energy can be accessed. Now, in the case of ATP, this enzyme which breaks down those phosphate groups is known as ATPase. Okay, now what you'll notice throughout energy systems is that enzymes most of the time will end with the word ase. So if you identify a certain word and it ends with ase, then you can bet that it's going to be an enzyme which is tasked with breaking one or many different types of energy bonds down. So it's ATPase which comes along, and once that comes along and breaks up that last phosphate group, okay, where the high energy resides, then we release that energy for the muscle to be able to use so that contraction can occur. Now, when that energy is released, this is known as an exothermic reaction. So not only do we release energy, we have a secondary component to that where we also release heat. So hence the word exothermic. So as the energy progresses, we release heat, which is one of the byproducts that we'll speak about when we move on to some of the energy systems. In addition to an exothermic reaction, we have what's known as an endothermic reaction. So this is just simply the opposite of an exothermic reaction. Here we are absorbing energy and heat. So this is where resynthesis of ATP is taking place, which we'll talk about in more detail over on the next slide. Now, once ATP has been broken down and energy has been released, the good news is that this process can be reversed. What is left when ATP is broken down is a molecule called adenosine diphosphate. Now, unlike triphosphate, we have now lost a phosphate group and we are just left with two of these phosphate groups. So hence the word diphosphate. So tri meaning three and di meaning two. There is also a form of adenosine monophosphate, mono meaning one, where that second phosphate group is broken up and we're just left with one. Now, what happens now is that we need to resynthesize ADP back into ATP. Now, provided that there is energy available, the body will resynthesize and add that phosphate group to make stored energy in the form of ATP. One of the shortcomings of ATP is that we only have around 40 to 50 grams worth stored within our muscles. Now, this equates to around 2 to 4 seconds worth of work. Of course, what we need to do then is we need to resynthesize that ADP molecule back into an ATP molecule. This is then stored energy ready to be used again. This can take place if we have energy which is available to us that we can break down, helping to resynthesize ATP. This is the point where our energy systems come into play, because the main aim of all of the energy systems, regardless of which one we're speaking about, is to simply add that phosphate group and turning ADP back into ATP. So it's three energy systems which we have within the human body, which are tasked with resynthesizing ADP and adding that phosphate group in order to make that stored energy again. However, just before we progress onto the individual energy systems, there are two tasks which I'd like you to complete just before we move forward. So the first task is simply to watch a very short video based on ATP and how it works within the human body. Hopefully this will start to give you some concept of how ATP is used and how we resynthesize energy. And then once we've watched that video, in your work booklet there are 3 pages, pages 1, 2 and 3, which I'd like you to complete. Here we're talking about what energy is needed for, the sources of energy that we consume, and then of course ATP, what this compound is, the enzyme which breaks it down, and also exothermic and endothermic reactions. So 5 or 10 minutes to get those tasks done, and then we'll start the 3 energy systems on the next slide. So hopefully the task which you've just completed and the video which you've just watched consolidated some of the basics regarding ATP, ADP, and how the two molecules interact based on the needs of the human body. But of course, now what we need to learn is how we resynthesize ADP back into ATP. And there are 3 energy systems which exist within your body in order to do that. The first one is the ATP-PC system. The second one is the lactic acid system, and the third is the aerobic system. Now, as we said, if energy is abundant, then the ADP will quite easily resynthesize back into ATP. However, the energy used depends on the intensity and the duration of the activity or exercise that you're undertaking. So when we resynthesize ATP, we can do this aerobically, which is with the use of oxygen, or anaerobically, which of course is without the use of oxygen. The first 2 energy systems, the ATP-PC system and the lactic acid system, are both anaerobic energy systems, meaning that we are resynthesizing ATP without the use of oxygen. So when you require short, intense and quick bursts of energy, it's the anaerobic energy systems which will help to resynthesize ADP back into ATP. However, when the duration is a little bit longer and the intensity is a little bit lighter, then we have time to deliver oxygen to the working muscle and therefore use the aerobic system, which is with the use of oxygen, in order to generate and resynthesize ATP. What's important to understand right at the beginning of energy systems is that this doesn't work in a step-by-step like manner where we innovate the ATP-P system first, then we go into the lactic acid system, and then eventually into the aerobic system. There is an interplay of all 3 energy systems occurring 100% of the time. However, what changes is the predominant energy system. So the energy system which you're calling on the most in order to resynthesize ATP. All right, so it's important to consider that we just don't go 1, 2, and then 3. We're using each one of the energy systems. However, it's the predominant energy system which we're interested in, providing that energy and metabolizing that energy during that particular moment in time. So we're going to learn more about what are the exercise intensities, what are the exercise durations. But of course, again, this is dependent upon the individual athlete and the fitness of that athlete as well. So without further ado, we're going to now go into each one of the individual energy systems, and we're going to look at the bioenergetics of each one of them and what occurs physiologically in order for ATP to be resynthesized. So once we've used our 2 to 4 seconds worth of stored ATP within the muscle cell, of course we've still got the ability to continue exercising, contracting and moving. And the reason for this is that we start now to resynthesize ATP from our energy systems. The first energy system, which is more often than not innovated, is the ATP-PC system. So this is an anaerobic energy system, and resynthesis takes place extremely rapidly because we don't have to wait for oxygen. So more often than not, this is the first energy system which we innovate, and we are using a fuel which we have stored in the muscle, which is known as creatine phosphate. So you may have heard of creatine before, which is a very popular sports supplement, and it's no different from what we supplement to what we find in the muscle. There are many forms of this supplement, but the one which is most popular is and also researched as one of the most effective is creatine monohydrate. And this is no different to the fuel which we're storing in our muscles in order to resynthesize ATP. So what happens here is that once ADP has been produced and we're in need of resynthesis, the first fuel which is called upon is creatine phosphate. Now what has to happen here is that creatine needs to donate its phosphate group over to the ADP molecule to make ATP. Now in order to do that, in order to break this fuel down, of course, we need an enzyme. So just like the enzyme which breaks down ATP, which was known as ATPase, this time we have a very different enzyme, which is known as creatine kinase. So this will do exactly what ATPase does, and it breaks up that phosphate group and then donates that energy, that phosphate, over to make ATP again. So now we have resynthesized ATP. Now, because this has happened without oxygen being present, this is often known as anaerobic metabolism. But also, because we haven't produced any byproducts during this, this has been byproduct free. This is what's known as anaerobic alactic. So this is meaning that there is no lactic acid which is being produced. So it's creatine kinase, which is the supplement which has broken up creatine phosphate and allowed that phosphate group to be donated in order to resynthesize ADP back into ATP. Now, this may seem like the perfect energy system because, of course, this is taking place rapidly. The fuel of creatine phosphate is already stored in the muscle, so it's very quick in order to donate that. However, we only have around 120 grams worth of creatine that we can store within our muscle. Of course, if we supplement this, we can increase the amount of creatine we have in our muscle, but only by 1 or 2 seconds worth of actual work that we can do during exercise. So in total, this equates for about 1 to 10 seconds worth of fuel, which we can use in order to resynthesize ADP back into ATP. After this 10 seconds, if we're exercising at high intensity, then of course you may notice that if you're ever doing full-on intense work such as a sprint, you can't really go at full pace for longer than 10 seconds. And the reason for this is because very quickly creatine phosphate will be depleted, and therefore the resynthesis rate will then start to slow down, and we'll then have to rely on our other energy systems in order to resynthesize ATP. So a question that you naturally might be asking now is, how do we get creatine phosphate back so that we can then start to use that fuel again? So when we think about this in terms of the gym, if we do something that is very explosive, like for example a 1 rep max or a maximal jump or punching a punch bag, something that is explosive, quick, we can't produce that same power, that same force output without a substantial rest. Now, what's happening here physiologically is that creatine phosphate is being resynthesized, and this is happening within the mitochondria. So if you know about mitochondria, you'll know that this is where aerobic respiration takes place. So within that mitochondria, one of the isoforms of creatine kinase is then resynthesizing the phosphate group back onto the creatine in order to make creatine phosphate once again. And this takes place over about 3 minutes worth of recovery time. So when you consider a 1 rep max bench press or squat, more often than not, when we're strength training, in order to get full recovery so that we have creatine phosphate back within our muscle and ready to use for the next set, we're talking about 3 minutes and above in order for that resynthesis of that fuel to take place. So therefore, we can start to use that in order to resynthesize ATP. So although this is an anaerobic energy system, it is still reliant upon the aerobic energy system in which to resynthesize that fuel. Okay, so following on from the schematic which we've just seen and the process which is occurring, there are a few things that we've still not covered relating to the creatine phosphate system. So there are things that you need to know and need to be aware of, which you may be asked in the exam. So we're going to go through these one by one, and we'll explain about each one as we progress. So as we've already identified, the fuel used for this system is creatine phosphate, and we find this within the muscle. As you've just again seen from the schematic there, we've got ATP being produced. Just one molecule of ATP is being resynthesized per one molecule of creatine phosphate. This does change as we progress through the systems, which you'll see in a few more slides. The duration, as we've identified, we have about a maximum of 10 seconds. The reason why it's 2 to 10 seconds is that, as we've already mentioned, we already have a supply of ATP between 2 and 4 seconds, depending on the individual, where we will be using that stored energy before we start to kick into our energy systems to resynthesize ATP. Of course, we've mentioned there that this energy system is taking place at high exercise intensities, where we're doing something which requires lots of force very quickly or explosively. Now, the site of reaction, we've just mentioned on the previous slide that aerobic respiration is taking place in the mitochondria. A different part of the muscle cell is what's known as the sarcoplasm, and this is where anaerobic respiration takes place. So if we're talking about anaerobic energy systems, then we're talking about the site of reaction being the sarcoplasm. As we've mentioned, when we're not using oxygen, this is what's known as anaerobic respiration. The enzyme, the controlling enzyme for this system was creatine kinase. Please do be careful to not identify ATPase. Creatine kinase is the controlling enzyme for creatine phosphate system. ATPase is the enzyme which breaks down ATP. There are no waste products, therefore this is an advantage of the ATP-PC system. And of course, when we're talking about sports which are exclusive to this system that want to train it, one of the outstanding examples, of course, is the 100-meter sprint. You know, when you think about Usain Bolt, who is, of course, the fastest man ever, and we think about the duration at which he can run at top speed, before he's even finished the race, he's beginning to slow down. So in terms of exercise physiology, this fits perfectly with the science relating to the depletion of creatine phosphate and therefore an inability to keep on forcefully contracting over periods longer than 10 seconds. We also have, of course, other explosive sports like shot put, weightlifting, but as well, like we mentioned regarding the interplay of the energy systems, of course, we're going to be using the ATP-PC system during specific phases of aerobic sports. So if we take, for example, a game of football, which of course lasts over 90 minutes, there are many occasions during a game, for example, a sprint for the ball, a last-ditch tackle, something along those lines, which will be using this system because it requires quick, explosive energy for the muscle to perform. Now, we've spoken about the recovery period. We said that around 3 minutes is required to get 100% recovery of creatine phosphate. But if we want to go again and maybe produce slightly less amounts of force, and maybe work on anaerobic endurance, then we can get 50% of our creatine phosphate back within 30 seconds. But again, just like any other biomotor ability, this can be worked upon with the right type of training over a period of time.
Okay, so just to explain the creatine phosphate system, what we'd like you to do now is turn to this page within your work booklet and using the graph, explain in as much detail based on the knowledge that you now have for the ATP PC system relating to the depletion of creatine phosphate and the depletion of ATP as we progress through time and intense exercise.
The second energy system that we're going to focus on is what's known as the lactic acid energy system. And just like the ATP PC system, this is an anaerobic energy system, once again meaning that we are resynthesizing ATP in the absence of oxygen. Now, it is important to understand that as soon as muscle contraction and exercise begins, the lactic acid system is helping to resynthesize ATP. But as we've mentioned in the ATP PC system, this system predominates because of how quick and efficient and easy it is to produce energy with the use of phosphocreatine. However, after that 10-second period when creatine phosphate begins to deplete, it's now when the lactic acid system begins to take over, especially if we want to continue with high intensity exercise. Now, the fuel in question when it comes to the lactic acid energy system is glycogen or glucose. Now, glycogen is simply just the stored form of glucose that we find in both our muscle and also within our liver. And glucose is broken down and ready to be used for uptake in the sarcoplasm or in the mitochondria. Now, when we are breaking down glycogen, once again, we require an enzyme in order to do that. So the breakdown of glycogen calls upon an enzyme known as glycogen phosphorylase. Glycogen phosphorylase helps to break down glycogen into glucose so that then we can start the process of anaerobic glycolysis. Now, anaerobic glycolysis simply just means the breakdown of sugar in the absence of oxygen, hence the word anaerobic. And whenever we see olysis, whether that be hydrolysis or whether that be glycolysis within sports physiology, then we're talking about the breakdown of a substrate. Now, substrate is just a fancy word for fuel. Now, once again, once we've broken down glycogen into glucose, then once again we require an enzyme in order to break that down. And we have an enzyme, what's known as phosphofructokinase, so PFK for short. And what this will do, it will break down glucose so that then we can resynthesize 2 to 3 ATP. Now, if we're using glycogen as our main form of substrate, then we produce 3 ATP. However, if we're relying on some blood-borne glucose that we get from our bloodstream, maybe, for example, if glycogen is depleted and low, then we only resynthesize 2 ATP. So the breakdown of glycogen, which by the way is referred to as glycogenolysis, or the breakdown of glucose, which we've already identified as glycolysis, without the presence of oxygen produces pyruvic acid. It's important as well to know that when we are breaking down glycogen and glucose, this is taking place in the sarcoplasm or the cytoplasm, and therefore, as we've already identified, this is where anaerobic respiration is taking place. Now, if we want to continue working at high intensities, for example, between that 10-second period and up to a 3-minute period, whether that be repeated sprints or anything along those lines related to sport or exercise performance, then pyruvic acid can do one of two things. It can turn into lactic acid, okay? And the importance of this turning into lactic acid means that we can continue to break down glucose to produce ATP when we're working at high intensities, or it can be broken down aerobically, which we'll speak about in the upcoming slides. Now, let's continue with the lactic acid system, because once we've produced pyruvic acid or pyruvate, then we want to keep contraction occurring at high intensities. In order for this to occur, we need another enzyme which breaks down pyruvic acid into lactic acid. And this enzyme is what's known as lactate dehydrogenase, or LDH for short. And this simply just breaks up that pyruvate and turns it into lactic acid. Now, it is a common misconception that lactic acid is the enemy, that lactic acid causes the muscle to burn, lactic acid causes the muscles to not function to their full potential. Now, of course, this is a byproduct of the system, hence the name of the system. However, what's important to understand is that lactic acid very quickly within the muscle cell will dissociate into lactate and also some hydrogen ions. So now, we use the word often lactate and lactic acid interchangeably, and they shouldn't be used interchangeably. This dissociation of lactic acid into lactate and hydrogen play very different roles in what happens next. Lactate actually has the ability to be turned back into glucose. Now, this doesn't happen in the muscle cell, this actually happens in the liver. So, if we want to continue exercising, then lactate can be transported to the liver where it is turned back into glucose and then delivered via the bloodstream back to the muscle cell. However, it's the hydrogen ions which cause the problem in terms of reducing the pH of our muscle. Now, when we reduce the pH of our muscle and acidity is increased, this is what causes the muscles to stop performing to their full potential. And this may even cause pain within the muscle, which you may have felt before when exercising at high intensities. So I think it's fair to conclude that the lactic acid energy system has many permutations which can take place dependent upon the intensity at which we're working. And this will hopefully become more clearer when we talk about the aerobic energy system next. However, the key takeaway points from this is that the fuel that we're using is glycogen or glucose. We are producing between 2 and 3 ATP, and we're doing this anaerobically without the presence of oxygen. The byproduct which is being produced is lactic acid, and of course that dissociates into lactate and hydrogen ions. And as we've already mentioned, it's a common misconception that it is lactate which causes the muscle to burn and to not perform as well and to not produce as much energy, but in actual fact it is the hydrogen ions which cause the reduction of that muscle pH. Lactate has got that ability to potentially turn back into glucose via the liver and then be delivered to the bloodstream. This is a process called gluconeogenesis, whereby lactate in the liver is turned back into pyruvate, eventually then turned back into glucose. So essentially what we're getting here is the reverse of glycolysis, and then once glucose has been produced, it is then delivered back to the muscle. Okay, so just to embed some of the key characteristics of the lactic acid energy system, we'll go through these step by step, which will hopefully help to refresh your memory and also consolidate your learning from the previous slide. So as we've already mentioned, the lactic acid energy system is an anaerobic energy system. Generally, this predominates between 10 seconds and 3 minutes. The reason why it kicks in after 10 seconds predominantly is because more often than not, the ATP-PC system will provide most of the energy for ATP resynthesis in that first 10 seconds of muscle contraction, especially when working at high intensities. So the fuel which we use for the lactic acid energy system is either glucose or glycogen. As we've already identified, glycogen is stored form of glucose that we find within our muscle and liver, and glucose is the broken down version that we can then convert via a process known as glycolysis. We produce 2 or 3 ATP per molecule of glucose or glycogen, so that being 2 for glucose and 3 for glycogen. The duration lasts between 10 seconds and 3 minutes, as we've just discussed. The intensity, given that it is anaerobic and we want a quick turnover of ATP, is more often than not high to medium. Now, when we get towards that 3-minute mark and we really do start to hurt and start to build upon our anaerobic endurance, then of course intensity may drop off a little bit, hence why that high/medium barometer is there. The site of reaction is the sarcoplasm. As we've already identified, all of anaerobic respiration takes place in the sarcoplasm, aka the cytoplasm. Enzymes controlling are phosphofructokinase, so this is breaking down glucose via glycolysis to produce ATP, and also lactate dehydrogenase, which breaks down pyruvic acid into lactic acid. And this allows for that process of glycolysis to continue anaerobically during the lactic acid energy system. The waste products, as we mentioned, lactic acid quickly dissociates within the muscle cell into lactate and hydrogen ions. Lactate is actually our friend in many ways, in that we can go through that process of gluconeogenesis and start to reproduce glucose, whereas hydrogen contributes to a lower pH of the muscle cell, which therefore reduces the amount of energy that we can produce, and also can increase the pain that we're feeling during exercise at high intensities. Now, when we talk about sporting examples, the 400-meter sprint is perfect. It fits perfectly into the duration of the lactic acid system, and of course needs to be done at high intensities in order to be successful within that sport. And then as well, we think about the interplay of the energy systems and think about certain phases during team sports. For example, a game of rugby where it may be end-to-end very quickly over quite a long period of time, for example, up to 3 minutes. Then, of course, we're going to be using the lactic acid energy system to maintain that intensity over a longer period. The same goes for a game of football, where it might be a wing back getting from one side of the pitch to the other and repeating that because the pace of the game is so quick. And then the recovery period is between 1 to 2 hours. The reason for this is that if we are resynthesizing and rebuilding our glycogen stores, then of course we have to wait to digest that food and get that glucose into our bloodstream so that we can continue in order to break down glucose anaerobically. Okay, so just to help to bring all that together, first and foremost, what we'd like you to do is to click on video 2, which you can find just below this lecture, and you can watch the video on the ATP-PC system and also the lactic acid system, where it will explain the processes that we've just been through and hopefully help to consolidate your learning in that regard. And also, there is a task within your work booklet, which is, as you can see on the screen, where I'd like you to identify some of the key characteristics of our anaerobic energy systems. So what are the fuels for the ATP-PC system and the lactic acid system? What are the controlling enzymes? What ATP yield do we get? What's the duration of each one of these energy systems? Just to help you consolidate everything that we've been doing so far. And then we can move on to our third and final system, which is the aerobic energy system. So pause the video, watch the video that we've given a link for, and then also complete the task which we've asked you to do. The third energy system is the aerobic energy system, and as the name suggests, we are now using oxygen in order to resynthesize ATP. And there are 3 distinct phases in which we go through during the aerobic system. Stage 1 is the aerobic glycolysis. Now, we're already familiar with this in terms of the lactic acid system, as there is nothing that changes here in terms of producing 2 ATP from 1 molecule of glucose. We then move into phase 2, which is the Krebs cycle, and again we'll speak more about that as we progress through this system, but we are producing 2 ATP in stage 2 of the aerobic system. And then stage 3 is the electron transport chain, where we are producing 34 ATP. So you can see there already there is a huge difference in the amount of ATP that we can resynthesize from 1 molecule of glucose when oxygen is present. So let's start with stage 1, which is aerobic glycolysis. And this process you're already familiar with, because this is exactly the same breakdown which occurred during the lactic acid system. So we'd have glucose, which is of course the substrate we're talking about for this energy system. And this will be broken down by an enzyme known as PFK. As we've learned, this is phosphofructokinase. And that breakdown of glucose produces and resynthesizes 2 ATP in the sarcoplasm. Now, what is different here is that when oxygen is available and intensity of exercise is moderate to low, Pyruvic acid doesn't need to be changed into lactic acid in order for glycolysis to keep on occurring. In aerobic glycolysis, when oxygen is present, pyruvic acid will just simply pass on into the mitochondria so that oxidative processes can take place. The second phase of the aerobic energy system is the Krebs cycle, and the Krebs cycle is taking the pyruvate, which is the product of glycolysis, and passing this onto the mitochondria in order to form acetyl-CoA. Acetyl-CoA stands for acetyl coenzyme A, and the whole purpose of the Krebs cycle is to change acetyl-CoA into ATP and producing carbon dioxide and water in that process. So what happens here, as we've mentioned in stage 1, when intensity is low enough and there isn't a backlog of pyruvic acid, there is no need to change that pyruvic acid into lactic acid because we have oxygen present in the mitochondria. So that pyruvate will pass on and then we will form acetyl-CoA. Now, of course, there are many reactions which take place within the Krebs cycle, but in terms of your preparation for the exam, what you need to be aware of is that the Krebs cycle produces a further 2 ATP. However, now we have the byproduct of carbon dioxide and water. The other point that we need to be aware of is that now this is happening in the mitochondria where all aerobic respiration takes place, and a specific part of the mitochondria which is known as the mitochondrial matrix. Okay? Now, as you can see from the diagram, we're also producing some hydrogen, and this allows us then to pass on to stage 3, where we can produce a lot more ATP in the third stage, which is known as the electron transport chain. The third and final stage of the aerobic energy system is known as the electron transport chain. Now, for your level 2 and level 3 examinations, you don't need to know the intricacies of the electron transport chain. But as the name suggests, what's happening here is that we are gaining and losing electrons within these reactions in order for oxidative phosphorylation to take place. Phosphorylation is simply just adding that phosphate group back onto ADP in order to make ATP. As we mentioned in stage 2, we are producing hydrogen ions and they are going into the electron transport chain where a huge number of reactions are taking place in the presence of oxygen, where we are now resynthesizing in total 34 ATP. So if we combine that with stages 1 and 2, one molecule of glucose is producing and resynthesizing, regenerating 38 adenosine triphosphate molecules. All of this, of course, again, is happening in the mitochondria. Oxygen is present, but the stage 3, the electron transport chain, is taking place in the mitochondrial cristae. And of course, if we combine hydrogen and oxygen together in the electron transport chain in order to produce these ATP, a byproduct that we're going to produce is H2O, which of course we all know as water. So the only harmless byproducts that the aerobic system is producing is water and carbon dioxide. Carbon dioxide, of course, we can easily get rid of through external respiration, provided we have a fully functioning respiratory system. So let's have a look at some of the characteristics of the aerobic system. We've had a look at the mechanistic views of what happens physiologically when we're breaking down these fuels in order to produce ATP. But some of these characteristics will help you to prepare for your exam and some of the questions that you might face. So as we've already identified, the aerobic system is providing continual energy supply in the presence of oxygen in order to resynthesize ATP. Okay, now we've mentioned with energy system 1, the ATP-PC system, and the lactic acid system, we've got energy resynthesis covered up to about 3 minutes. So more often than not, if we want to extend our activity, extend our exercise at moderate to low intensities beyond that 3-minute mark, then we're going to rely predominantly on the aerobic system in which to resynthesize ATP. Now, as we identified, the fuel which is being used during aerobic system, we mentioned glycolysis at stage 1, which is the breakdown of sugar and glucose into pyruvate. But one thing we didn't mention is that we can also use fat as a fuel. Now, whether we use glucose or fat in the aerobic system is dependent upon a few things, but most of the time this will depend on the exercise intensity. Generally, at around 25% of our VO2 max, so this is at relative walking pace, we're using about 85% fat in order to fuel that exercise. However, as intensity increases, for example, if we go into a jog or a run, then we're using about 50-50. So 50% of the fuel that we resynthesize ATP in the presence of oxygen will be from glucose and 50% from fat. However, as we go up the intensity scale and we say, for example, are running just below an aerobic threshold at about 85% of our VO2 max, then we're probably using about 85% glucose, 25% fat. So which fuel we use is dependent upon the intensity of exercise. There are other factors like nutrition status and also the fitness of the athlete, but just for keeping it simple for now, exercise intensity plays a part when it comes to fueling the aerobic energy system. Now, when it comes to energy yield, when we use 1 molecule of glucose in the presence of oxygen and we go through the 3 stages, aerobic glycolysis, the Krebs cycle, and the electron transport chain, we are producing 38 ATP per 1 molecule of glucose. Now, if we compare that to fat, we are actually producing 129 per 1 molecule of fat. Now, of course, looking at this, it may seem advantageous that if we use fat as a fuel, then we are resynthesizing, nearly 3 times as much fat versus glucose. However, there are advantages and disadvantages to both of these fuels being used aerobically. So, first off, glucose is much quicker in terms of its production. We produce and resynthesize ATP much quicker when glucose is the fuel. So, of course, that has advantages in terms of sports performance. And when we're using fat as a fuel, this actually takes nearly 15% more oxygen uptake. Therefore, our respiratory system and our VO2 max needs to be of a certain standard where we can use fat efficiently. So, there are factors at play, and of course, glucose and fat both contribute to resynthesis of ATP, but of course there are determining factors as to which one is more advantageous than the other. So just to give you an example, if we're using glucose or glycogen as the fuel, then this is a finite fuel source. So we only have around 3,000 calories of which we can store in our muscle, in our liver, which we can use and break down for energy during aerobic respiration. Once this has been burnt and we've used those energy supplies, then unless we are feeding carbohydrate during performance, which of course we can do, for example, during marathon running, then we will be exhausting all of our glycogen and glucose stores. On the other hand, fat, if we're using this as a fuel, we have pretty much an inexpendable amount of adipose tissue, stored fat, up to around 120,000 calories worth, which we can call upon in order to produce and resynthesize ATP. So, of course, there are certainly advantages and disadvantages, but of course, when we're talking about the aerobic energy system, we're also talking about dual fueling. We're not just talking about burning glucose at one particular stage and burning fat at another. We can burn both at the same time in order to resynthesize ATP. So I suppose just like the energy systems, there is a predominant fuel source depending upon the intensity or the stimulus that we put upon our body. Of course, the duration of the aerobic system, meaning we have a continual supply of oxygen, and therefore this can take place between 3 minutes and hours and hours and hours. Again, this may depend on the fitness of the athlete, but of course we have that continual aerobic supply to our working muscle and to the mitochondria, where we can keep on burning those fuels provided that they are available. The intensity, as we've mentioned, is medium to low in relation to the ATP-PC system and also the lactic acid system. However, it is important to recognize that elite marathon runners are still running at ridiculously high intensities and yet still burning aerobic fuels in order to resynthesize ATP. And yet they've got the ability and the fitness to use the aerobic system at much higher intensities and therefore utilize that glucose and that fat to resynthesize ATP. So the fitness of the athlete does play a huge part as well on the interplay of the energy systems. The site of reaction we've identified, there are two sites of reaction. The mitochondrial matrix is where the Krebs cycle is taking place and where we're producing 2 ATP when we're using glucose as a fuel, and the mitochondrial cristae is where the electron transport chain is taking place. The enzymes involved for the breakdown of glucose during glycolysis is phosphofructokinase, and the enzyme which is breaking down fat, there are a few, but for the context of your level 2 and level 3 examination, lipase is the enzyme which will break down fat. The waste products, although they are easily gotten rid of within the body, are CO2 and H2O, so that's carbon dioxide and water. And of course, when we're thinking about sports which lend themselves to the aerobic system, we're thinking about team sports lasting over a longer period of time. Generally, the more duration we have in a particular sport means that the aerobic system will likely be predominant. So football, of course, lasts over 90 minutes. A marathon is taking place over the course of hours. Okay, and then of course long distance cycling, such as the Tour de France, again is going to rely heavily on the aerobic system. And lastly, the recovery period for the aerobic energy system is around 24 hours, given that if we've trained over a long period of time or performed over a long period of time, then we simply just need that time to refuel and also for the muscles to recover before we use that system again. Okay, so that brings the aerobic energy system to a close. With regards to the fuels which we're using and the interplay between glucose and fat, there is a fantastic video which I would like you to watch to help you further understand this. And this is identified below this lecture in video 3. So if you click on that link and watch that video, hopefully that will give you some insight into the dual fueling between glucose and fat and some of the factors which play a part in that. And hopefully what's also becoming apparent is that if we have a keen interest in nutrition, then it is absolutely pivotal that we have this basic physiological knowledge, because of course when we're talking about supplying the athlete with the right type of nutrients, the right type of fuels, we need to have a basic understanding of the human physiology and the energy systems in order to make the right choices based on the sports, the activity, the intensity, and the fuels required. And lastly, just to bring about the learning for the aerobic energy system, if you can fill in the characteristics of the aerobic energy system in the worksheet at the back of your booklet, then that will bring about all of the energy system characteristics and a nice revision tool for you to prepare for your exam. So if we revisit the objectives which we identified at the start of the lesson, we can see now that we've identified and described ATP, adenosine triphosphate, within the human body. We've looked at the key characteristics of the three energy systems, which are the ATP-PC system, the lactic acid energy system, and the aerobic energy system. And we've also understood, hopefully, how these energy systems function in relation to different sports, exercise, and of course intensities and durations and so on. What's important to remember here is that the energy systems have an interplay. They are not working in isolation. They are working all together. However, it's which one is predominant based on the characteristics of the exercise that you're undertaking. And as mentioned, this is a very, very important topic moving forward if we're looking to prosper as a personal trainer. So let's bring all of this learning together now with the final task, which is a formative assessment on the energy systems. You can access this on the link below under formative assessment for the energy systems. Click on the link, complete the quiz, and of course, if you wish, you can retake that just for practice in order to prepare for your level 2 and level 3 examinations. Good luck.